Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science. And in this video, we're going to do an example of complex line integrals. So complex line integrals really aren't that much different from real line integrals in that we pretty much evaluate them by parameterizing. But the only real difference is that we're in the complex plane, so we have the imaginary unit I possibly floating around somewhere. But it really doesn't change a whole lot. It's just pretty much a different way of viewing the same thing, actually. So here we want to evaluate the integral from 0 to 1 plus I of z squared dz. So from 0 to 1 plus I, we can just think of that as the straight line path between the point 0 and the point 1 plus I in the complex plane. And in the complex plane, so plain old 0 is still just the origin, so we have x and then we can say iy if we want to be pedantic about it. So here's 0 at the origin. And then 1 plus I is really the point 1 comma 1, because 1 plus I is really 1 plus 1 times I. So this 1 comes from this one here, and then this 1 comes from this one here. Okay, so that's what's going on there. And if we were to plot that in the complex plane, we would get this point right about here. So basically we're integrating sort of along this path of this line here from 0 to 1 plus I. So the arrow indicates the direction. So we go from 0 to 1 plus I, and we're integrating along this path of this line here. So we have a complex line integral. So what we want to do is just kind of parameterize along this path. So remember that z, we can think of z as x plus I, z is x plus iy, where x represents the real part and y represents the imaginary part. So if we want to parameterize z, we can think of z as a function of t, which essentially means that x and y are both functions of t. So we have z of t equals x of t plus I times y of t. Okay, and then what we can do is look at our path here and see, okay, what kind of path do we have? Well, we just have a straight line that basically goes from 0, 0 to 1, comma 1. So we go from 0, 0 to 1, comma 1. So there are many different ways we can parameterize, but perhaps the best or simplest one is going to be, okay, let's just say x of t equals t, and y of t also equals t, where 0 is less than or equal to t is less than or equal to 1. So if we go with that, then what we're going to have in our case is z of t equals t plus t times I. Okay, so for our integral then, we're going to have the integral from 0 to 1 of, now z is t plus ti, so we can drop that parentheses t notation and just say z equals t plus ti. Okay, so then z squared is going to be t plus ti, quantity squared. Now what we can do is actually, we can make this a little bit easier on ourselves, so we can say t plus ti equals t times the quantity 1 plus I. So if we want to square everything, so this squared is going to be this squared, which is actually the same thing as t squared times 1 plus I quantity squared. Okay, so this is t squared times 1 plus I quantity squared. So that says 1 plus I. Let's go ahead and fix that. So t squared times 1 plus I quantity squared. But there is something that we have to be careful about now. So we are integrating, so this is t squared, and then 1 plus I quantity squared. Now we are integrating with respect to t, so we have to change this to dt, but dt just itself is not quite right, because we have to see, okay, well we have dz, and we know that z is t plus ti, so we have to use this to actually figure out what dz is in terms of dt. So it's basically just like when we do a line integral in the real plane, or when we make any kind of substitution, you know, we have to change our variables, so we have to express d the new, we have to express d the old variable in terms of d the new variable. So dz is going to be something times dt. Okay, so that's what we have to figure out. So nothing really new here, just sort of in a different place that we're doing this. So if z is t plus ti, which actually we can write as 1 plus I, that quantity times t. Now 1 plus I is just a constant, right? So if we want to say dz, then that basically means take the derivative of this over here with respect to t and then slap a dt on it. Okay, so since 1 plus I is just a constant multiple, then what we're going to have is just plain old 1 plus I dt. Because again, 1 plus I is a constant multiple, so what if we had like 3t? Then the derivative of that with a dt on it, which is also called the differential, would be 3 dt. Well, here we don't have 3, we have 1 plus I, but nothing changes. 1 plus I is still a constant, okay, because I is a constant, and 1 is a constant, so 1 plus I is a constant. So it might look a little weird if you're new to this because of the 1 plus I, but the point you want to keep in mind is it's really just a constant. Okay, so dz is going to get replaced with 1 plus I dt. All right, so that's what's happening there. So now we have another 1 plus I up here, actually, and then dt. So what we actually end up with is the integral from 0 to 1 of t squared times 1 plus I cubed dt. So let's go ahead and go to the next page and evaluate that. So we'll rewrite it there so it's easier to see. So we have the integral from 0 to 1 of t squared times 1 plus I cubed dt. Now again, 1 plus I is a constant, so 1 plus I cubed is also a constant. So let's pull it out of the integral. So we are integrating from 0 to 1 t squared dt. And now this is pretty much just a plain old calculus 1 type integral, except with the goofy constant multiple out in front. And then if we integrate t squared, we get 1/3 t cubed. And we're evaluating from 0 to 1. So this is 1 plus I cubed times 1/3 times 1 cubed minus 0 cubed, right? Evaluate at the top minus evaluate at the bottom. 1 cubed is 1, 0 cubed is 0, so this entire expression in here is just 1. And then our final answer, therefore, is 1 plus I, that quantity cubed, all divided by 3. Dividing by 3 because of the 1/3 out here. Okay, so this has been an example of doing a complex line integral. I hope you found this video helpful, and thank you for watching.